All right, greetings and welcome to AP Environmental Science's first lecture on whatever media you happen to be on, whether it's a laptop or a phone or anything that you can access the internet to. This is a brief introduction to astronomy. I'm just going to give you a few things that I think is nice to have as background information about our planet and how it is situated, how it was formed. Hopefully this will have a little bit of overlap with some of the things you learn in chemistry, and if not, you'll get a little bit here of it now. So what I'm going to do is I'm just going to annotate through a couple of slides for you and give you some ideas about how it all happened. How did we get here? Well, take a look at this. There's a lot of stuff going on here. We've got the Big Bang Theory. That's our current most up-to-date idea of how everything started. And time begins about 15 billion years ago, which is an incredibly long time ago. 15 billion years. You'll notice that in the first second alone, look at that, like first second, so time begins here, right? And by 1 second, what do we have? We already have the formation of all these elementary particles, different types of bosons and electrons and quarks and good stuff. Those are going out in a very, very, very small amount of time, and they are then gathering into, you can see them here, they're coming together, they're gathering up here in the top left image. Quarks are gathering into the different hadrons. Remember, neutrons and protons are a class of particles called hadrons that are composed of quarks. And quarks come in actually 6 different flavors. If you remember that, that's up, down, top, bottom, strange, and charmed. Our proton here is composed of 2 up quarks and 1 down quark. And those that took me in chemistry would know that I put a little arrow for up quarks here, and that's a down quark. And neutrons have 2 down quarks and 1 up quark. Sort of fascinating, interesting stuff. So neutrons having no net charge, being neutral, and protons having that +1 charge. Took a little bit longer, not too much though. By 3 minutes we had nuclei, and so here you can see the formation of the hydrogen nucleus, which is essentially just that 1 proton, and the helium nucleus, much more complex, with 2 protons and 2 neutrons for most of those guys. Took a little longer. You'll notice 300,000 years before the universe cooled to the temperature, right, the low temperature of 10,000 degrees Celsius, and that allowed those first atoms to form, which means the electrons were now in orbit around them. Took a billion years or so more. Look at this, proto-galaxies and galaxies. This is the important part, gravitational attraction. Remember, that's one of our 4 fundamental forces in the universe that we know of. We have gravity, we have electromagnetism, we have the strong nuclear force and the weak nuclear force. Weak nuclear associated with beta decay, or the release of an electron, and the strong nuclear force, the force of attraction, holding those protons and neutrons together. So there we go. All that gravitational attraction creating stars. First stars are forming, giant stars, massive stars. Key thing to remember is that stars are chemical element factories. So the elements fuse, undergo fusion to the point of iron. Iron's about the last element that are made in stars. And after that, because iron is so stable, we don't get the higher elements. We don't get things like uranium and radon and all those wonderful heavier elements. We get those when stars explode. So when stars undergo a supernova, collapse in on themselves and explode violently, that's when we get the rest of the elements above iron and nickel. And there's our present day. We have 15 billion years or so later. We have our planets and stars that were formed from those earlier stars, those proto-stars that were the big early stars that lived a short, violent life. Here's a stellar factory. This is Eagle Nebula, where new stars are being formed. These are giant gas clouds, hundreds of millions of light years across. And there's new suns being formed there and new solar systems around those suns. So that's the nebula, or the remnants of a dying star, birthplace for new stars. And that might be a little crazy to think about, but when you look at this image, you'll look in here, and here's our sun right here. Here's a sun-like star. I'll kind of just circle that for us, right? But this doesn't even portray how much bigger these supergiants are. These blue supergiants are sometimes millions of times larger than our star. And if you think about our star in a minute, we'll see like Earth is like a tiny little, just a pinprick in terms of size. And so even a sun as big as ours, which is not that big, would be easily capable of destroying itself and making stardust that would eventually become our planet. So, what is so cool about our sun? Our sun is a long burning sun. It's been around for about 5 billion years, and we think it's going to have about 5 billion more. So it allowed complex life to form on our planet because we had a lot of stability over those 5 billion years. Started out not as bright as it is now, so it took a little while to get up to that brightness or intensity, but over time it's been very consistent. Ultimately, it will become a red giant, and we hypothesize that our first inner 3 planets, which happen to include us, will be consumed, but not before our atmosphere is completely swept away and the oceans are boiled away and all that good stuff. Rest assured, not supposed to happen for billions of years. And our ultimate demise was most likely for our sun is going to be a white dwarf. So just a small little ball of products that are left from fusion that are just sort of continuing to fade out and glow over time. Again, blue supergiants, these are the biggest stars. When they explode, black holes are created and just all kinds of amazing things that are going on there. All right, so here's our sun. Fusion is the process as opposed to fission, which is breaking apart. We've got a picture here of an atom bomb, a uranium bomb. Here's some magnetic ejecta from the sun, some coronal solar flares and things like that. But again, consistency of our solar output has been key for complex life. And what else is so cool about the Earth? Well, okay, so we've got a sun that works well for us. We've got a sun that burns pretty evenly over time. It's not going to go supernova on us. It's been around a while and it will continue to be around. But also, Earth is just the right distance, so this is not to scale. The Earth is on average about 92 million miles away from the sun, and it's just in the right range. It's a range that what we call, well, let's just kind of, I guess, put a little arrow here, the green zone. So the green zone, and that's where you're just far enough from the sun so that water can exist as a liquid phase, but not so far that water will essentially just be a solid. So it gives us liquid phase water. So here we'll put our notation H2O in the liquid phase. Put a little smiley face. That's good. That's good for us. So we have the sun that burns pretty evenly over time. It's a long burning sun. We have a planet that's just the right distance from our sun to provide liquid water, which allows life to be possible as we know it. And we've also got these guys here, and in particular this guy here. So we'll put some eyes here. How about that? And we'll make that like a little mouth and a tongue sticking out just for good measure. So there's Jupiter. Jupiter is actually a very cool guy. That's our big brother. There's some funny little ears there on Jupiter, and I don't know, we'll give him like a little fez or something like that for a hat. So there's Jupiter. Jupiter's our big brother. Jupiter protects us. So when you have different asteroids, here's an asteroid coming in, or meteorites, Jupiter pulls them in. So, nice and hungry there. So what it's done is it's basically allowed Earth to have a pretty catastrophic free upbringing. The Chicxulub meteor crater that hit at the Yucatan Peninsula, we think wiped out the dinosaurs 65 million years ago. Those are pretty rare. Those are rare events. We have a lot of little meteorites that hit us, but the big guys get pulled in, and even Saturn, right? Saturn's pretty big, and you can have these little meteorites and comets and stuff that fly around the solar system get taken up by that guy. So thanks to Jupiter, our big brother. We also can't see it here, but there's a moon. We have a moon. It's pretty small, and that moon is also instrumental in tidal regulation and some other important things for Earth as well. So more on that a little bit later this unit. Off motions of the heavens. What does the Earth do? It rotates about its axis around the sun, gives us seasons, and finally the moon. That's again responsible for tides, so helps to regulate the climate on the planet as well, and does some other key important things. So these are 3 things that we'll talk more about in detail a little bit later on in the class. Okay. So that was kind of a quick introduction, and
recognize that the very molecules that make up your body, the atoms that construct the molecules, are traceable to the crucibles that were once the centers of high-mass stars, that exploded their chemically enriched guts into the galaxy, enriching pristine gas clouds with the chemistry of life, so that we're all connected to each other biologically, to the earth chemically, and to the rest of the universe atomically. That's kind of cool. That makes me smile. And I actually feel quite large at the end of that. It's not that we are better than the universe. We're part of the universe. We're in the universe, and the universe is in us.
We're not the center of the universe, but we are in it and of it, trying to figure it all out. There's so much we know, and yet so much we still don't know. We hold on tight as our little planet goes hurtling through space, around the sun, around the galaxy, around the universe. Don't forget to look up. There's so much to see, so much to know. Where do we begin?